Hey guys, this is Srini and you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In this tutorial, I'm going to talk about edge filters for your image processing. And there are a variety of edge filters that are available to you in Python. And most of them are spatial filters. Like for example, Robert, Sobel, Shar, everything I'm showing on the screen here, they're all spatial filters, meaning they are some sort of a convolution with your image or some sort of a matrix multiplication with your original image. There are also filters that are based on the frequency domain. For example, you take your image, convert it into, take it into a frequency domain by applying a, for example, discrete Fourier transform. And then on the frequency domain, you're actually applying some sort of a mask. So this is exactly how a high pass filter or low pass filter actually works. And I'll save that for a different day. So for now, let's actually focus on Robert, Sobel, and these other filters that I am showing on the screen. Although I should mention, I'll not go into a lot of depth on all of these. Again, as usual, I'll try to use plain English as much as possible to describe them. And also, you should realize that, for example, Sobel is almost like an extension of Roberts. Okay, so they're all related. And let me take a few minutes to talk about each of them, and then we can actually implement them in Python. And I keep using the term implement them in Python. It's actually not implement, but we're going to use it because someone else already implemented this algorithm. Okay, so we are not rewriting this thing. So let's go to this drawing board so I can explain what was the first one, the Roberts filter, right? So the Roberts filter again is a convolutional filter. Okay, so again, convolution is you have your image and your image is defined by a bunch of pixels in X and Y, right? And at each pixel you have a specific value or multiple values if it's an RGB image. Now you apply a convolution filter. So for example, if that filter is a 2 by 2 filter, okay, then you have like a 2 by 2 matrix that you're multiplying at every pixel. Central pixel is multiplied by this, okay, around the central pixel. So Roberts is again it's a 2 by 2 filter. Okay, so convolutional kernel is a 2 by 2 convolutional kernel, and it's designed to approximate the gradient of an image. Okay, or in a way, think of it as doing differentiation at every pixel. Okay, and the way it is actually done is by computing the sum of differences, okay, between these diagonally adjacent pixels. That may be a mouthful or a very large sentence, but in summary it highlights the regions of it highlights the edges, right? Obviously, that's the whole purpose. Now, if you look at the Sobel operator, there are two operators, okay, both rotated by. In fact, let's actually draw this a bit bigger so you can see it. So if this is operator number one in the x direction, so let's call this like operator one gx, and there is another operator in the y direction. Okay, so gx and gy. Let's call this y. Now, what is the difference? This operator is plus 1, 0, 0, minus 1. And this is rotated. This is exactly same numbers, but rotated by 90 degrees. So 0, plus 1, minus 1 here, and 0. As you can see, here it's aligned along this direction. Here it is aligned along this direction. Okay, so that's why we are applying these two. Okay, and they are designed, as you can see, to respond to edges running at 45 degrees. Okay, to this pixel grid. Okay, so what do we do once we get these two? Well, the actual the magnitude is actually calculated by, as you can imagine, gx gy squared and then square root, right? So this is exactly how and as you can see, this is a very easy computation. So this is a very fast operator. Okay, so now let's actually switch to Python and see how easy it is to implement this. In fact, I changed my mind. Let's actually quickly talk about the other filters before actually jumping into Python, because in Python, implementing each of this filter is literally one single line. So I don't want to jump back and forth between talking about them and then implementing them. So let's actually cover the other few, starting with we did Roberts, and the next one is Sobel. Yeah, and Sobel filter is very similar to Roberts, except this is uh, 3 by 3 matrix. Okay, so previously we had plus 1, 0, 0, minus 1, right? 2 by 2. And here you have 1, 2, 3, 0, 0, 0, and minus 1, minus 2, and minus, I think this is minus 1. And this is 1 again. Sorry about that. So 1 to 1, minus 1, minus 2, and minus 1. Okay, and 0, 0, 0. This is it. This is your kernel along x direction, or operator along x direction, and along the y direction for Sobel, you have this exactly the same way as before. 1 to 1, and you have 0, 0, 0, and you have minus 1, minus 2, and minus 1. This is it. Okay, and of course there is also, if you want, again, our actual final implementation is, or the magnitude is gx squared plus gy squared, just exactly as before, and this is your magnitude over there. Okay. And you can also calculate the gradient direction, right? I mean, anytime you have this, you can actually calculate the angle by actually theta equals to your arctan of these two values, right? Gy over gx. So you can do a lot of math, but basically it comes down to the fact that this is the operators for Sobel. Now, char is less common. Scharr, but it's also available. In fact, when you apply all of these, you see very similar results. So you makes you wonder why you have all these selections. But again, they're all available in scikit image. So char is pretty similar to, again, think of it very similar to Sobel. So there is one on x-axis. So you're looking at the differentiation along x-axis, and then y equals to 0, and then the next one dx equals to 0 along y-axis, and then along y-axis, it's equals to 1. Uh, so as you can see, these are designed to identify gradients independently along x-axis and along y-axis. Okay, and the performance of char is very similar to Sobel. So in all honesty, I don't even ever try using char. I most of the time I do Sobel or Canny. These are my top two, and then Roberts occasionally. Okay, and moving on, another one, Prewitt operator. And again, like all of these, Prewitt is also a gradient based, or it's actually doing looking at the derivatives. In fact, it looks very similar to Sobel. So if I write my Prewitt, I think that's how it's spelled. Prewitt operator is very similar, like I said. So again, you have these two along x and y directions, and Prewitt is 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Okay, and gy is again rotated 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. So as you can see, they're all in a way kind of based on Roberts implementation. Okay. And Farid, this screen is getting a bit busy. So Farid is again kind of similar. Okay, except in this case they actually propose a two pairs of kernels, not just one pair. Yeah, so in this case they propose two pairs. One is for interpolation and the other differentiation, right? So far we looked at Sobel and others, they're all like derivatives based. So that one is already here. So Farid, one is interpolation, okay, and the other one is used for differentiation. Okay, again, you can read original papers on these. I'm sorry, but this is at a high level. Okay, so the interpolation kernels, they're all fixed size. You cannot choose these, and for differentiation, it is 7 by 7 kernel size. Okay, and this is Farid. And finally, we have Canny. Okay, Canny is again one of the most commonly used ones. So let me take another 30 seconds to 1 minute to explain what it is. So Canny is a bit complicated because it's not just one convolution, it's actually multi-steps. Okay, so when it comes to Canny, now step number one is apply Gaussian filter. Okay, it applies a Gaussian filter, And what does it do? It smooths the image. Yeah, and why do they do that? The primary goal is to remove noise. Okay, otherwise it can be a bit difficult. So that step is remove noise. And then the step number two is finding intensity gradients. Okay, uh, intensity, if I can write it, finding intensity uh, gradients. Now, uh, the edge can be aligned in any direction, right? This is why we use Sobel and others, in a diagonal way. So the Canny uses four filters to detect the horizontal, vertical, and the diagonal edges. Okay, in this blurred image, because now we are dealing with a blurred image. Okay, so the edge detection operator, and you can use any of these like Roberts, Prewitt, or Sobel. uh, and again, I'm not really sure what scikit image actually uses, but technically you can use any of those. And it returns this again. You end up with your gx and gy, like I mentioned earlier, and then gx squared plus gy squared under root. This gives the magnitude of your intensity gradient. And then step number three is what they call non-maximum suppression. Okay, uh, suppression. And again, not going into detail, what this basically does is think of it as edge thinning technique. Okay, it's basically applied to find the largest edge. Otherwise, you may see these double edges. Okay, if you again, in fact, I think you may have actually seen this if you tried this Canny in the past. When you apply initially, you don't like these thresholds, and then you look at this. Double edges or so. So this step is to do non-maximum suppression, and finally apply double threshold. Okay, so apply double threshold. This is where actually, if you ever used Canny in Python, you probably supplied two values for the threshold. This is exactly what you're doing. Yeah, this double threshold actually determines the potential edges. Okay, so this is what the double threshold step actually does. And finally, there is a step called edge tracking by hysteresis. Okay, and again, this is the key part, because this is where the user input parameter actually comes into the picture. So this step is the double threshold is there to remove any of the remaining edge pixels. Okay, by providing an accurate window. Okay, because after non-maximum suppression, you may still end up with okay, I have an edge like this, and then a faint. Sorry, that was supposed to be a faint edge, but anyway, we'll probably see this while we're applying the Canny in a minute. Okay, and the fifth step, finally, what it does is edge tracking by hysteresis. Okay, this is in a way finalizes the detection of edges by minimizing or suppressing all the ones that are weak or not connected to strong edges. Okay, so this is again, I'm just going to call this hysteresis. Okay, so this is how Canny actually works. So now I think it is time to jump into our Python, Spider IDE to actually apply all of these. So let me bring the Spider IDE again. As usual, in order to save time, I typed this ahead of time. So let's go ahead and paste part of it. So again, all the libraries up here that are required to plot, that are required to convert our images. I'm not sure we'll be converting, so we may not need that. But anyway, to display the images and all of it. And our filters are, in fact, I don't probably need to import filters at all, because I'm going to import the filters separately right here, because these are the ones we plan on implementing. So here, so from scikit image.filters, import Robert, Sobel, Shar, Prewitt, and Farid. Okay, so these are the filters that we are going to apply, and I am not doing Canny because I'll save that after this, because Canny is slightly different compared to all of these, right? These are all pretty straightforward. So to apply this again, because we've already imported it, all I'm doing is, okay, Roberts image, Sobel image, Shar, apply it on my image. That's pretty much it. And now let's go ahead, and the best way to visualize these is, let's actually use OpenCV. Sorry, where is, did I type it? Yep. So let me go ahead and copy it here. So we are going to display our Roberts image, Sobel, Shar, Prewitt, and Farid images. Okay, and let's apply this. And again, implementation so easy as you can see. Someone already did the work for us, so all we're doing is importing the appropriate filters. Okay, so let's go ahead and run it. And I'm applying this on an image called BSC. So I have way too many things showing up on my other screen. So let me pull one by one. One thing I did not show, which I should have, actually, let me kill. Sorry about this. I should have actually opened up the original image. There's no point in doing this, actually. And our original is called just img, right? So let's do our original image. So one more time. Okay, so there you go. So my original image, if I can find it, there you go. Here is the original. Okay, and let's start by looking at one by one. Okay, so Roberts. Here is the Roberts. It actually worked very well, right? Including these faint ones right around here. These two, I don't see them much there, but it's a pretty good one. And one thing you notice is you see some of these that are, are strong, some of these are weak. Again, this depends upon the direction, the orientation, and many other factors. So that is that. And Sobel is right here. Again, if you look at these two, they look almost identical, almost identical. That's why I always, because the implementation is fast either way, I always use Sobel. Okay, now moving on to Char. Between Char and Sobel, again, they look very similar. I mean, some edges are strong, some edges are weak, but they're exactly almost, I can't even tell the difference anymore. Okay, so that is our Char, and what else do we have? Prewitt, there you go. So this is our Prewitt, and again, if you look at the difference between this and Sobel, I can't tell any much difference. So after all that lecture, I'm saying, okay, go ahead and use Sobel. Farid, this is one of the recent ones that got implemented. And again, I'm not sure how good it actually shows up on your screen, but uh, I mean, if I enhance the numbers, if I can change the brightness and contrast of this Farid image, that would look very similar to the image that I have here on the right-hand side, which is the Sobel filter. So in summary, there are many of these available. Maybe depending on the type of image that you're working with, some may turn out to be better than the others. But again, now you know how to implement this if it comes down to it. Okay, so now let's actually remove all this Sobel and all of this stuff. Okay, and let's also do that. Remove that and just apply Canny Edge. Okay, and the way you apply Canny Edge detector is you first define this. Okay, Canny Edge cv2.canny, and that's where we are done. Oh, I shouldn't have deleted the cv2 imshow. Let me copy these two lines that are required to show the image and add our cv2.imshow, and this would be Canny and Canny Edge. And you see these numbers here, 50 and 80. These are all for this double thresholding step, right? I mean, the step that I talked about right here. So this double thresholding part, this is where you need to supply these values. And this is where we struggle a lot. I struggle a lot. I'm not sure about you. I struggle a lot because no number seems to be ideal for me. Okay. So let me go ahead and run this. And again, I should have shown the original image. Okay, original IMG. Okay, there you go. That should work. And let's have a look at our original image and the Canny edge. I mean, it looks great, but as you can see, there is a lot of double edge going on right there. Okay, and there is a lot of, I don't like this image, and I don't think you'd like it too. What happens if I change this to, I don't know, 30 to 120? This is the problem, right? I mean, we don't know what works well. Okay, that still looks pretty bad. This is my issue with Canny. 180. I mean, some of these edges are kind of okay, but this is again, honestly, this is the reason why I always use Sobel. Now, one thing is with Canny, it would be nice if you know what the median numbers are, for your lower and upper threshold. And in a way, if you really want Canny, but in an automatic way, you can kind of do that. Here are 4 lines of code that you can use to define your auto Canny. So it's calculating your lower. Let's actually define a sigma of zero point 0.3, for example. And I'm also calculating median. So median equals to or numpy, and there is a median in there. So all I'm trying to do is find the median value, in our image, and then define some sort of a multiplication factor to the median value, and getting my lower, and then also defining my upper threshold. Lower is again 0 to whatever that, and upper I'm actually getting a value between 255. So I'm basically defining my lower histogram value here and upper, instead of predefining it as 30 and 180, because I don't know what works on my image. Okay, so this is if you want, you can call this auto canny. Okay, so that's which means CV2. Let's also look at this image, auto canny. Okay, and the variable auto canny. Okay, so now let's actually look at these images. And okay, there is the canny, and here is auto canny. Okay, slightly better, but I'm not sure how much better. Yeah, that's and if you are curious what the values are, so where are we? Lower is 103, and upper is 192. So it's almost like, okay, if I type 103 and 192, you should get exactly the same images in both cases. Okay, so except we are just doing this in an automatic way. That's it. Okay, so apologize for this long tutorial. I was hoping this to be like less than 10 minutes, but obviously it went over. But I hope you find this to be useful. Again, there are many varieties. If you just want the simple solution, just use Sobel. Canny seems to work very well, but again, you need to fine tune your parameters. Auto, in a way, kind of gets you there, but still you need to fine tune it to make sure you're getting the right, you're getting the desired result, with your approach. Anyway, thank you very much. I hope you found this tutorial to be useful. As usual, I request you to please subscribe to my channel. It keeps me very encouraged to create more content. And thank you for your time.